Deep beneath the crimson dust of Mars, locked inside rocks untouched for billions of years, scientists have uncovered something extraordinary. Traces of organic material, the very building blocks of life. Not random chemicals, not mere byproducts of stone and fire, but complex signatures that resemble what we know from Earth's biology. For generations, we have looked up at the night sky, asking the same question. Are we alone? We built telescopes to pierce the void. We launched probes across millions of miles. We listened for whispers among the stars. And all the while, the answer may have been waiting on the world next door. Tonight, we embark on a journey across history, science, and discovery. From ancient myths of Mars to the first robotic footsteps, from false alarms to breakthrough evidence, and finally to the present moment, when NASA may have found what humanity has sought for centuries. Prepare yourselves. This is the story of how we came to the brink of answering one of the oldest questions in human history. Has life been found on Mars? Like and subscribe as we begin. Mars has always been more than a planet. Long before we knew what it truly was, it lived in human imagination. To the Babylonians, Mars was Nergal, a god of war, famine, and fire. To the Greeks, it was Ares, fierce and destructive. And to the Romans, who gave us its modern name, Mars embodied the very essence of conflict. Even in the night sky, its rusty glow seemed to promise bloodshed. But Mars was not only a symbol of fear. In cultures across the world, it was seen as a messenger. Ancient Indian astronomers tied it to courage and energy. In China, it was known as the fire star. Wherever it appeared, it stirred awe and unease. For millennia, that was all Mars was, a light moving among the stars. But then came the telescope. In 1609, Galileo Galilei pointed his small refractor toward Mars. What he saw changed everything. No longer just a red pinprick, Mars revealed itself as a world. A tiny disk with dark and light patches. Other astronomers followed. By the 17th and 18th centuries, Mars became a place to be mapped, measured, and compared. The first great mystery appeared at the planet's poles. Astronomers noticed white caps that grew in winter and shrank in summer. Were these made of ice, like Earth's? If so, could Mars have seasons, weather, maybe even life? By the 19th century, Mars became the center of one of astronomy's greatest controversies. In 1877, Italian astronomer Giovanni Schiaparelli trained his telescope on the red planet during a rare opposition, when Mars came unusually close to Earth. He drew detailed maps of the surface and described long, thin lines crossing the globe. He called them canali, meaning natural channels. But in translation, canali became canals. The word changed everything. Canal was not natural. Canal was built. American astronomer Percival Lowell seized on the idea. Wealthy and obsessed, he founded an entire observatory in Flagstaff, Arizona, to study Mars. Through his telescope, Lowell believed he could see a network of artificial waterways, stretching for thousands of miles. To him, they were proof of an advanced Martian civilization, desperately trying to irrigate a dying world. Lowell published book after book, his sketches of canals filling newspapers, firing the imagination of the public. Writers took the idea and ran with it. H.G. Wells wrote The War of the Worlds, imagining Martians not only surviving on their own planet, but invading ours. Edgar Rice Burroughs created the John Carter of Mars novels, filled with alien kingdoms and strange adventures. Mars was no longer a star. It was a neighbor, a mystery, a world alive. But science has a way of correcting our dreams. By the early 20th century, telescopes improved. The canals began to vanish. What Schiaparelli and Lowell thought they saw were illusions of the eye, shadows, streaks of dust, tricks of light. Mars was not laced with irrigation. It was barren, desert, empty, or so it appeared. In 1965, the first close-up images arrived from NASA's Mariner 4 probe. The photos were devastating. A bleak landscape covered in craters like the moon. No cities, no rivers, no signs of civilization. The dream of Martian empires collapsed overnight. And yet, the mystery endured. If Mars once had ice caps, and if it showed traces of seasonal change, could it not also have once had water? And if water, then perhaps, just perhaps, life? NASA pressed on. By the 1970s, the question of Martian life had become urgent. If life existed beyond Earth, even as microbes, it would change everything we knew about biology. So NASA designed a mission unlike any before, Viking. In 1976, Viking 1 and Viking 2 touched down on the surface of Mars. Each carried a suite of experiments carefully built to test for life. The landers scooped up Martian soil, mixed it with nutrients, and watched for chemical reactions. And the results? Astonishing. One test came back positive. Gases released that seemed to suggest metabolism, as though invisible microbes had begun to feed. But the other instruments found nothing. NASA, cautious and conservative, announced that the evidence was inconclusive. To the world, the verdict was simple: no life on Mars. But in the quiet corners of the scientific community, debates raged. Some researchers insisted Viking had, in fact, detected life, primitive, microbial, hidden in the dust. Others argued it was chemistry alone. Nearly 50 years later, we still debate those results. The Viking missions left us with a tantalizing mystery. If Mars is dead today, was it always dead? Or did we arrive too late to catch life in its prime? For decades after Viking, the consensus was grim. Mars was cold, dry, and lifeless. Missions were scaled back. Interest waned. Yet Mars had one final card to play. It was not as dead as we thought. In 1996, NASA scientists studying a Martian meteorite discovered on Earth, a rock known as ALH 84001, announced something shocking. Inside the meteorite, they found tiny shapes resembling fossilized bacteria, along with traces of organic molecules. The world was electrified. Life from Mars in a rock in our own hands. But the excitement did not last. Critics argued the microscopic features could be formed by non-biological processes. The debate rages on even today, unresolved. Still, the meteorite rekindled our fascination. By the 2000s, orbiters equipped with more powerful cameras revealed Mars as a world shaped by water. Vast canyons, dry riverbeds, deltas, and shorelines emerged from the images. Billions of years ago, Mars had lakes, rivers, even oceans covering much of its northern hemisphere. Water, the essential ingredient for life. Suddenly, the idea of a living Mars no longer seemed like fantasy. In 2012, NASA landed the Curiosity rover inside Jezero Crater. This machine, the size of a small car, carried instruments capable of probing Martian rocks at the molecular level. Within months, Curiosity delivered groundbreaking news. It had discovered complex organics, carbon-based molecules locked inside ancient rocks. These were not proof of life, but they were the raw ingredients. The kind of chemistry that, on Earth, led to biology. Even more intriguing, Curiosity detected seasonal changes in methane gas levels in the Martian atmosphere. On Earth, most methane comes from living organisms. Could Mars still harbor life deep underground, releasing faint whispers of gas into the sky? Then came Perseverance. In 2021, NASA's most ambitious rover yet touched down in Jezero Crater, a place where an ancient river once flowed into a lake. Jezero was chosen for a reason. River deltas are natural collectors of life's signatures. If Mars ever hosted microbes, their chemical traces might still be trapped in the sediments there. Within months, Perseverance found something extraordinary. Using its suite of cameras and spectrometers, it examined rocks that showed strange textures, branching patterns, tiny holes, and features resembling microbial mats seen on Earth. Some rocks even displayed what scientists called leopard spots, light patches ringed by dark halos, eerily similar to mineral patterns created by biological activity on Earth. The rover's instruments detected organic molecules in these rocks, far more complex than anything Curiosity had found. Layered sediments, rich in carbon compounds, told a story of long-vanished water and chemical activity. NASA scientists, careful not to leap ahead, described the findings as potential biosignatures, possible evidence of life. They stopped short of a declaration. But between the lines, one message was clear. Something remarkable was buried in Jezero Crater. Then, in 2023, another breakthrough. Perseverance confirmed that some of these organic molecules were arranged in patterns that geology alone struggled to explain. They hinted at structure, at organization, the hallmarks of biology. And in 2025, after years of careful analysis and cross-checking, the verdict is becoming undeniable. The simplest explanation for the combined evidence, the methane cycles, the organics, the textures in rock, is that Mars once supported microbial life. The announcement is cautious, as science always is. NASA has not yet proclaimed we found life. But to many scientists, the case is already stronger than ever before. For the first time in history, humanity may be standing on the threshold of answering a question older than civilization itself. Are we alone? But what exactly did NASA find? And how do scientists know these discoveries point to life? To answer, we need to step back and explain what counts as a biosignature. On Earth, life leaves fingerprints everywhere. Microbes produce gases like methane. They create microscopic textures in rocks, burrow through sediments, and form mats that fossilize into layered structures called stromatolites. They leave behind organic molecules, chains of carbon and hydrogen, sometimes arranged in intricate ways that are extremely unlikely to arise by chance. When scientists study Mars, they look for these same fingerprints. Not proof of life, but signs that point toward it. Perseverance has found organics locked inside sedimentary rocks, the type that forms in water. These organics include aromatic compounds, ring-shaped carbon molecules that, on Earth, often form from biological processes. The rover also detected sulfates and phosphates, minerals tied to energy cycles used by microbes. Even more compelling are the textures in certain rocks. Tiny pits and veins crisscrossing the surface look strikingly like patterns created by microbial colonies in shallow water on Earth. And then there's the methane mystery. Mars' atmosphere shows spikes of methane gas that rise and fall with the seasons. On Earth, 90% of methane comes from life. Volcanoes can produce methane too, but Mars shows no current volcanic activity. Something else is at work. Each piece of evidence on its own is ambiguous. Organics can form without life. Methane can come from geology. Rock textures can be mimicked by chemistry. But together, the puzzle grows harder to dismiss. The weight of evidence leans toward biology. Still, scientists are careful. History has taught caution. The Viking experiments once seemed to detect life, only to fall into doubt. The Martian meteorite once sparked headlines, only to fade under scrutiny. This time, NASA moves slowly. The word life is withheld, not because it isn't possible, but because it must be beyond doubt. That is why Perseverance is collecting samples, tubes of Martian rock and soil sealed for return to Earth. In the coming decade, those samples will arrive, carried home by the Mars Sample Return mission. There, in laboratories far more advanced than any rover, the final tests will be made. But already, many in the scientific community whisper what cannot yet be shouted. We may have already found life on Mars. On February 18, 2021, millions of people around the world held their breath. A spacecraft entered the thin Martian atmosphere, traveling at more than 12,000 miles per hour. Heat shields glowed, parachutes unfurled, rockets fired in a delicate ballet of precision engineering. And then silence, until a voice crackled through mission control. Touchdown confirmed. Perseverance is safely on the surface of Mars. Cheers erupted. Humanity had landed its most advanced rover yet. A robotic scientist designed not just to explore, but to seek out the fingerprints of ancient life. Perseverance was not sent to just any location. Its target was Jezero Crater, a site chosen with care after years of study. Satellite images revealed a striking feature: the ghost of a river delta, frozen in stone. Billions of years ago, Jezero had been a lake, fed by flowing water. And where rivers meet lakes on Earth, life flourishes. If Mars ever hosted microbes, this delta was one of the best places to look. The rover's instruments were cutting edge. A drill capable of collecting core samples, sealed in tubes for a future return to Earth. High-resolution cameras able to spot details finer than a grain of sand. A laser spectrometer to analyze the chemistry of rocks. Even microphones to capture the whisper of Martian wind. But one of the most surprising finds came early in the mission. As Perseverance examined the crater floor, it found rocks with peculiar patterns. Light-colored patches surrounded by dark halos, giving them a spotted appearance. Scientists nicknamed them leopard spot rocks. At first glance, these patterns might seem ordinary, but to geologists they stood out. On Earth, similar halos can form when minerals are altered by microbial colonies, tiny organisms changing the chemistry of the rock as they live and grow. Of course, Mars is not Earth. Chemical processes alone can also create spots and halos. Yet the discovery sparked a wave of excitement. For the first time, Perseverance was seeing structures that hinted at past biological influence. These were not fossils, not proof, but they were clues, subtle whispers written into stone. The rover drilled into the rocks, storing precious cores in its titanium tubes. Someday, perhaps in the 2030s, those samples may be flown back to Earth, where laboratories can search for definitive evidence of ancient Martian microbes. But Perseverance did not stop with the leopard spots. As it moved closer to the river delta, the rover encountered layered sediments, fine grains stacked in delicate bands, exactly like those formed in riverbeds on Earth. Within those layers were carbon-based molecules, organics, the same family of molecules that, on Earth, are associated with life. The story of Mars was becoming clearer. A world that once had rivers and lakes, rocks that bore strange chemical halos, organic molecules preserved in sediments. Piece by piece, the puzzle was aligning toward a breathtaking possibility. Mars may once have been alive, but the evidence was not only chemical or geological. It was also atmospheric. Mars is a world of silence, Its atmosphere is a whisper compared to Earth's, a fragile envelope of carbon dioxide, so thin that a breeze on Mars would barely rustle a sheet of paper in your hand. And yet, this thin veil of gas has carried one of the most intriguing mysteries of planetary science: methane. On Earth, methane is everywhere. It seeps from wetlands, bubbles up from ocean floors, and escapes from the digestive systems of countless animals. More than 90% of methane on our planet is produced by life. That is why, when telescopes on Earth first detected faint traces of methane in the Martian atmosphere in the early 2000s, scientists were electrified. Could this be the breath of microbes still alive beneath the Martian surface? But almost immediately, the mystery deepened. Methane does not last long in an atmosphere. Sunlight and chemical reactions destroy it within a few centuries, sometimes much faster. That means if methane exists on Mars today, it must be replenished. Something somewhere is making it. But what? NASA's Curiosity rover added fuel to the fire. In 2013, its onboard instruments sniffed the Martian air and found methane. Not just once, but in varying amounts. Some seasons, the methane rose. Other seasons, it fell. Then, Curiosity detected sudden spikes, bursts of methane far higher than background levels, as if the planet had exhaled in short, powerful breaths. For scientists, this was both thrilling and perplexing. Methane can be produced by life, but it can also come from geology. On Earth, methane sometimes escapes when water reacts with certain minerals deep underground, creating a gas that seeps to the surface without any help from biology. The challenge is that both explanations fit the data. And from millions of miles away, distinguishing between microbial metabolism and geological chemistry is one of the hardest tasks in science. Yet the puzzle only grew stranger. The European Space Agency's Trace Gas Orbiter, a satellite designed to study Mars' atmosphere with exquisite precision, reported finding no methane at all in the global atmosphere. How could Curiosity see methane at ground level, while a satellite above saw nothing? One possibility is that methane is released in localized bursts, plumes that dissipate quickly before they rise high enough to be detected from orbit. If true, this would suggest active regions on Mars, where gas still seeps from the subsurface. And the implications are enormous. If the methane is geological, it means Mars is still geologically active, with liquid water interacting with rock deep underground. That alone is fascinating and increases the chances for habitable environments. But if the methane is biological, then even now, in the cold and radiation-bathed Martian soil, life may endure. Not grand forests or animals, but hardy microbes, clinging to existence in hidden pockets beneath the surface. For decades, we have pictured Mars as a dead world. Yet the air itself seems to whisper, perhaps not. Perseverance carries instruments capable of helping unravel this mystery. By analyzing gases trapped in rock samples, future studies on Earth could reveal isotopic fingerprints, subtle differences in atomic weight that can distinguish methane made by geology from methane made by life. Until then, the question lingers. Each whiff of methane is a clue, a thread leading us deeper into Mars' hidden story. And this story is not told by the air alone. It is etched in stone, locked within meteorites that have journeyed from Mars to Earth, carrying secrets across the void. Long before our rovers set wheels on Martian soil, pieces of Mars had already come to us. Every so often, an asteroid slams into Mars with such force that fragments of rock are ejected into space. Some of these fragments drift across the solar system for millions of years until gravity pulls them down to Earth. We call them Martian meteorites. They are rare, only a few dozen have been confirmed. but each one is priceless. They are natural samples from Mars, delivered free of charge by the cosmos itself. One of these rocks would change the way we think about life beyond Earth. In 1984, in the icy wastelands of Antarctica, a team of meteorite hunters stumbled upon a dark, potato-sized rock. It was cataloged as Allen Hills 84001, or simply ALH 84001. At first, it seemed ordinary, but years later, in the 1990s, scientists analyzing it made a stunning announcement. Inside this meteorite were microscopic structures, tiny, worm-like shapes embedded in the rock, resembling the fossils of bacteria. Alongside them were mineral patterns and organic molecules, eerily similar to those produced by living organisms on Earth. In 1996, NASA scientists declared before the world that they may have found evidence of ancient Martian life locked inside ALH 84001. The news sent shockwaves through science and culture. Newspapers ran headlines announcing, "Life on Mars." President Bill Clinton addressed the nation, calling it one of the most important discoveries in human history. For a brief moment, humanity stood on the edge of cosmic confirmation. We were not alone. But science is cautious. Almost immediately, other researchers challenged the claim. Could the shapes in ALH 84001 be non-biological? Could chemical processes, operating in the harsh conditions of space, produce similar patterns? The debate raged for years. Some argued that the microscopic structures were far too small to house DNA or RNA, the genetic material of life as we know it. Others pointed out that certain minerals in the meteorite could form abiotically, without life's influence. As evidence was re-examined, confidence faded. The scientific consensus shifted. Today, most researchers believe ALH 84001 does not provide definitive proof of Martian life. But the meteorite remains extraordinary, because whether or not it contains fossils, it carries a message. Mars and Earth are connected. Rocks travel between our worlds. Microbes, in theory, could as well. This idea is called panspermia, the possibility that life, or its seeds, can hop from planet to planet, carried by rocks blasted into space. If life arose on Mars first, it might have spread to Earth. Or if Earth birthed life, perhaps some of it hitched a ride to Mars. Either way, ALH 84001 forced us to see the story of life not as bound to one planet, but as part of a cosmic network, fragile yet enduring. And it was not the only Martian meteorite to raise eyebrows. Others, too, have shown unusual chemical signatures, organic molecules, and textures that tease the possibility of biology. None have been conclusive, but together, they form a chorus of whispers. Whispers that life may not be confined to Earth. For scientists, these meteorites were tantalizing hints. But to truly know, we needed to go back to Mars itself. We needed rovers like Perseverance drilling into rocks, storing samples, and searching for biosignatures. And as Perseverance dug deeper into Jezero Crater, NASA prepared for the next great leap. Not just to study Mars from afar, but to bring Mars home. For centuries, we have gazed at Mars through telescopes, imagining civilizations, canals, or barren deserts. In recent decades, we've sent spacecraft to orbit and rovers to roll across its surface. Each mission has sharpened the picture. Mars is no longer a distant mystery. It is a world we know intimately. But despite all our progress, one barrier remains. The greatest tools of science, the electron microscopes, the advanced spectrometers, the genetic sequencers, are here on Earth, not millions of miles away on Mars. No matter how advanced our rovers become, they are still limited compared to what human laboratories can do. That is why NASA and its partners have set their sights on the boldest goal yet: to bring Mars to Earth. This is the Mars Sample Return Mission. Perseverance has already begun the first step. As it explores Jezero Crater, it drills into carefully chosen rocks and seals the cores into titanium tubes. Each tube is no larger than a marker pen, yet within it may lie the key to one of humanity's oldest questions. Dozens of these tubes will be left on the Martian surface, cached like treasures awaiting collection. The next step is one of the most complex engineering challenges in history. A future lander, likely arriving in the 2030s, will touch down near Perseverance's cache. It will carry a small fetch rover, designed to pick up the sealed samples and deliver them to a rocket, the first rocket ever to launch from another planet. That rocket, the Mars Ascent Vehicle, will blast off from the surface, carrying the samples into orbit around Mars. Waiting there will be another spacecraft, the Earth Return Orbiter, which will capture the precious container and begin the long journey home. If all goes to plan, those Martian rocks and soils will arrive on Earth sometime in the mid-2030s. For the first time in history, scientists will hold pieces of Mars in their hands, unaltered, uncontaminated, ready for the full power of Earth's laboratories. The stakes are immense. In those samples, we may find microfossils, unmistakable evidence of organisms that lived billions of years ago. We may find organic molecules arranged in patterns that scream of biology. Or we may find nothing conclusive, confirming instead that Mars was once habitable but never inhabited. Even that outcome would be profound. Knowing the difference between potential and reality would reshape our understanding of life's rarity in the universe. But the possibility of discovery also raises questions of caution. What if the samples contain active microbes? What if, against all odds, Martian life still clings to existence, waiting to be awakened in Earth's labs? NASA and international partners have considered this carefully. The samples will be contained in multiple layers of protection, designed to withstand the journey and prevent contamination in both directions. Specialized facilities, more secure than those used for handling deadly viruses, will be built to examine the material. For some, these precautions echo science fiction fears of alien plagues. But for most scientists, the risk is low. If microbes do exist on Mars today, they would likely be so adapted to their harsh environment that Earth's conditions would be lethal to them. Still, the symbolism is striking. For the first time, we would be holding in our hands not just pieces of another world, but perhaps the evidence of another genesis of life. Mars Sample Return is not just a mission. It is a turning point, a moment that may divide human history into a time before we knew and a time after. And yet, even as NASA plans this daring retrieval, other missions and instruments are pushing the search forward in parallel. Because while rocks may hold fossils of the past, the atmosphere may still hold whispers of the present. And beneath the surface, there may be something more, reservoirs of water where life could endure to this day. On the surface, Mars looks dead, a world of rust and dust, frozen under a thin sky. But appearances can be deceiving. Sometimes the most important stories are hidden beneath the ground. For decades, scientists have suspected that Mars still holds vast reserves of water, locked away as ice. Orbiting spacecraft have mapped enormous sheets of frozen material just beneath the soil. In some places, glaciers lie buried under blankets of dust, preserved like time capsules from a wetter age. But in 2018, something extraordinary was announced. Using radar instruments aboard the European Space Agency's Mars Express orbiter, scientists detected what appeared to be a subsurface lake, a body of liquid water buried more than a kilometer beneath the southern polar ice cap. It was a stunning claim. For years, researchers debated whether the signal truly represented water, or if unusual layers of frozen minerals were tricking the radar. But then, additional studies revealed not just one, but multiple bright reflections, suggesting an entire network of underground reservoirs. If confirmed, this means that beneath the frozen desert, Mars may still hold pockets of liquid water, the single most important ingredient for life. But liquid water on Mars is not like a lake on Earth. The temperatures are far below freezing. To remain liquid, the water would likely be briny, saturated with salts. On Earth, such environments seem hostile. And yet, even here, life persists. Deep beneath Antarctic glaciers, in the pitch-black waters of Lake Vostok, microbes survive, sealed off for millions of years. In salt-saturated ponds of Chile's Atacama Desert, extremophiles thrive where nothing else can. If life can adapt to these conditions on Earth, could it not also adapt on Mars? This is why the search has increasingly turned underground. The surface of Mars is bombarded by radiation, stripped of its protective atmosphere long ago. Any life on the surface would be short-lived. But below ground, shielded by rock and ice, the story might be different. Drilling, however, is one of the hardest challenges in planetary exploration. Perseverance can drill only shallow cores, just a few centimeters deep. To truly access potential habitats, we would need to bore meters, even kilometers, into the crust. A task far beyond today's technology. Yet hints continue to surface. In 2020, NASA's InSight lander deployed a heat probe, hoping to burrow into the Martian soil. Though the instrument struggled, its mission provided invaluable data about subsurface temperatures and geology. Meanwhile, orbiters continue to refine maps of buried ice, suggesting that future astronauts might someday dig directly into water-rich ground. The stakes are high, because if Mars still harbors living microbes, this is where they would likely be, tucked into aquifers, clinging to warmth, shielded from radiation. And the implications extend beyond Mars. If a frozen, barren planet can still host life underground, what does that mean for the icy moons of Jupiter and Saturn, where oceans hide beneath thick crusts of ice? Worlds like Europa and Enceladus may be teeming with activity, their hidden seas even more promising than Mars. But for now, our focus remains on the red planet. Mars' underground realms represent the frontier, the last refuge where life may linger. And as we search below, we must also look back to the surface features that hint at an ancient, watery past, and to the tools that allow us to read the story of a planet written in stone. Mars is a world of stone. Craters, cliffs, canyons. Everywhere we look, the red planet reveals itself as a geological record. But rocks are more than scenery. They are memory. They preserve, sometimes for billions of years, the traces of what once was. On Earth, some of the oldest evidence of life is not bones or shells, but subtle imprints. Fossilized microbial mats known as stromatolites, layered formations built by colonies of microorganisms, growing in shallow water. These structures are still found today, forming in tidal pools and lagoons, whispering across deep time. Scientists believe that if Mars ever had microbial life, its traces would most likely resemble these simple signatures. Not grand fossils of creatures, but patterns in the rock, textures that cannot be explained by geology alone. This is one of Perseverance's most important tasks: to scan the Martian landscape for biosignatures. It carries cameras with microscopic resolution, able to reveal fine layers in sediment. It has spectrometers that can identify minerals associated with biological activity, like carbonates and sulfates. Already, Perseverance has seen rocks that resemble ancient lakebed deposits, with fine laminations, delicate bands suggesting sediments settling in calm water. Some contain organic molecules, the carbon-based building blocks of life. Others show chemical variations that hint at possible microbial interaction. But here lies the challenge. Geology is a master imitator. Chemical reactions, evaporation, and crystallization can create patterns that mimic life's handiwork. For scientists, the task is to separate the echoes of biology from the tricks of chemistry. On Earth, this process is already difficult. Researchers debate ancient rocks even here, where we have far more data. On Mars, the challenge is magnified. That is why Perseverance's samples are so crucial. Only in Earth's labs can we determine whether these structures are truly fossils or geological illusions. Yet the tantalizing possibility remains that somewhere in Jezero Crater, in a rock no larger than your hand, lies the imprint of a Martian microbe, a fossil older than any life form on Earth, a record not of our story, but of another. To understand whether life could have existed on Mars, we must solve another puzzle: its climate. Today, Mars is bitterly cold, with average temperatures around -80 degrees Fahrenheit. Its atmosphere is thin, offering little warmth or protection. Yet everywhere we look, the surface is carved by water. Valleys stretch for hundreds of miles. Deltas fan out like fingerprints. Minerals form only in the presence of liquid water. How could a frozen desert once have hosted rivers and lakes? For decades, scientists have struggled with this paradox. The young sun, billions of years ago, was dimmer than it is today. With a thin atmosphere, Mars should have been locked in ice. And yet, the geology insists otherwise. One theory suggests that Mars once had a thicker atmosphere, rich in carbon dioxide, trapping enough heat for liquid water to flow. Another proposes that giant impacts from asteroids periodically warmed the planet, melting ice and creating short-lived wet periods. Still, others argue that volcanic eruptions may have released bursts of greenhouse gases, triggering cycles of habitability. Whatever the mechanism, the fact remains: for at least part of its history, Mars was wet. And where there is water, there is the possibility of life. But Mars could not hold onto its climate forever. Slowly, it lost its magnetic field, the invisible shield that once protected it from solar winds. Stripped of this defense, the atmosphere was eroded away into space. Rivers dried. Lakes froze. The planet transformed from a blue world to the red desert we see today. This raises another haunting question. If life ever began on Mars, did it adapt to this change? Did it retreat underground, finding refuge in aquifers and ice? Or was it wiped out, leaving behind only silent fossils? The climate mystery is more than scientific curiosity. It is a mirror. It shows us how fragile habitability can be, how a world that once teemed with rivers can be stripped bare. And it forces us to ask, if Mars lost its atmosphere, could Earth one day suffer the same fate? The search for life on Mars has been filled with triumphs, but also with false alarms. In the 19th century, astronomers were convinced they saw canals. In the 20th century, the Viking landers seemed to detect lifelike activity in Martian soil. Each time, excitement surged, only to fade under scrutiny. Even today, the danger of misinterpretation remains. Take methane, for instance. On Earth, it is a clear biosignature, but on Mars, it could be entirely geological. Similarly, organic molecules are essential to life, but they can also be formed without biology, through purely chemical processes. This is why scientists are cautious. The line between evidence and proof is razor thin. A single misstep could mislead the world, shaping beliefs for decades. Yet false alarms are not failures. They are steps in the journey. Each one sharpens our tools, deepens our questions, and prepares us for the moment when the signal is real. Because the day may come, perhaps soon, when the evidence is undeniable. When the whispers from rocks, air, and ice converge into a single, clear voice. Until then, each misleading clue is part of the process, guiding us closer to the truth. If we want to imagine what Mars may have looked like when it was alive with water, we need only look back into Earth's own history. 3.5 billion years ago, Earth was not the lush green world we know today. There were no forests, no animals, no humans. Instead, Earth's surface was covered by vast oceans, with volcanic islands and shallow lagoons. The atmosphere was different, filled with carbon dioxide, nitrogen, and only faint traces of oxygen. And yet, in this alien environment, life took root. Microorganisms thrived in shallow waters, building stromatolite reefs and altering the chemistry of the oceans. Slowly, life transformed the planet, paving the way for everything that followed. When we look at Mars, we see a reflection of this era. The Jezero Crater, with its dried-up delta, resembles Earth's Archean shorelines. The minerals Perseverance detects, clays, sulfates, carbonates, are the same that Earth's earliest microbes once called home. This parallel is profound. It suggests that life may not be a rare accident. It may be a natural consequence when conditions are right. If Earth and Mars both developed the ingredients of habitability at the same time, then perhaps both worlds also gave rise to biology. But while Earth's life flourished, Mars' life may have struggled. As the climate worsened, Martian organisms would have faced a desperate choice: adapt or perish. If they adapted, they may still exist today, hiding in protected niches underground. If they perished, they left behind only chemical fingerprints in stone. To study Mars is to glimpse our own planet's youth. And in doing so, we are reminded that the story of life is fragile, balanced on the knife edge of planetary fate. Most of our search on Mars has focused on the past. Fossils, rocks, dried riverbeds. But what if Mars is not just a story of extinction? What if something still lingers? The most promising habitats are not on the surface, but below it. Just a few meters underground, conditions change dramatically. Shielded from radiation, protected from extreme cold, there could be pockets of liquid brine, salty water that refuses to freeze, even in Mars' harsh climate. In 2018, radar instruments on the Mars Express orbiter detected something extraordinary: a bright reflection beneath the ice at the planet's south pole. The signal looked remarkably like liquid water, trapped beneath layers of ice and dust. Later studies questioned whether it truly was water, or perhaps unusual clays. But the possibility remains: a subsurface lake on Mars, a potential refuge for life. On Earth, we find microbes in astonishing places. In Antarctic ice, deep within salt mines, even kilometers underground in dark aquifers. These extremophiles prove that life does not need sunlight, forests, or oceans. All it needs is energy, water, and time. This is why every detection of methane on Mars excites scientists. Methane is unstable in the atmosphere. It should break down quickly. Yet, telescopes and rovers have recorded plumes that appear and disappear. If this methane is geological, produced by reactions between rock and water, it's still a clue to a dynamic planet. But if even a fraction of it comes from microbes, it would be revolutionary. To confirm it, we will need more than robots. We will need boots on the ground, drills in the ice, and instruments capable of reaching depths that rovers cannot. Until then, the question remains suspended. Is Mars truly dead, or is it quietly alive beneath the dust? Rovers like Perseverance are marvels of engineering. They can drive, drill, and analyze. They are patient, precise, and untiring. But they are not human, and on Mars that matters. A trained geologist standing on the surface could achieve in a single afternoon what it takes a rover months or years to accomplish. Humans could climb cliffs, sample dozens of rocks, and notice subtle features that machines overlook. They could repair instruments, adapt strategies, and pursue the unexpected. But beyond efficiency, there is something deeper. Human presence transforms exploration. It is one thing to see an image of Mars on a screen. It is another to hear the crunch of dust beneath your boots, to feel the silence of another world pressing in around you. NASA's Artemis program, aiming to return humans to the moon, is the stepping stone. From there, missions to Mars become more realistic. The journey will be long months in space, radiation exposure, isolation. The surface will be harsh, with dust storms and freezing nights. Yet history tells us, humanity does not stop at the shoreline. We cross oceans, we climb mountains, we launch into skies. Mars is the next horizon. When humans finally arrive, their task will not just be exploration. It will be confirmation, to hold a Martian rock in hand, to split it open and see a fossil, or to detect life still moving within it. That moment would be the most profound discovery in human history. Until then, Perseverance keeps watch. It waits, it listens, it gathers, preparing the way for the day when human eyes, not cameras, look upon the red planet with their own awe and wonder. Whenever Mars enters our imagination, it is not just as a place to visit, but as a place to stay. Science fiction writers have dreamed of terraforming Mars for over a century, transforming the dry, frozen world into something green, blue, and alive. The idea is simple, at least in theory. Restore Mars' atmosphere. If its air were thicker, it could trap heat. If the planet warmed, ice would melt, rivers might flow again, and perhaps Mars could sustain life on its surface once more. Proposals range from the modest to the monumental. Some suggest releasing greenhouse gases, such as carbon dioxide trapped in polar ice, to thicken the atmosphere. Others imagine giant orbital mirrors reflecting sunlight onto the surface. Still others dream of directing asteroids rich in ammonia toward Mars, seeding it with nitrogen for a breathable sky. But the challenges are immense. Mars may not have enough carbon dioxide to make its air thick again. Without a magnetic field, solar winds would strip away any new atmosphere as quickly as it was built. Terraforming might take centuries, or even millennia. It might require technology we have not yet invented. And yet, the vision persists. To terraform Mars would not only be an engineering feat, it would be a philosophical one. It would mean turning a dead planet into a second cradle for life. It would mean humanity had learned not just to explore worlds, but to create them. But there is a tension. If Mars already harbors life, even if only in the form of microbes beneath the soil, should we alter it? Should we preserve Mars as it is, a natural world with its own biology? Or do we have the right to shape it in our image? Terraforming forces us to confront a question we have never faced before. Are we explorers, gardeners, or conquerors? Discovery is never only about the object we find. It is also about how it changes us. If NASA were to confirm life on Mars tomorrow, real, undeniable life, the consequences would echo far beyond science. Religions would interpret it in different ways. Some might see it as proof that creation is vast, that the divine spark is not confined to earth. Others might wrestle with what it means for humanity's place as the center of a sacred story. Philosophy would also be shaken. For centuries, we have debated whether we are unique. If life arose independently on Mars, then the universe is not silent. It is fertile. Life is not a miracle, but a rule. The night sky would no longer be empty. It would be crowded with possibility. For ordinary people, the shift would be deeply personal. Children in classrooms would grow up knowing that we are not alone in the cosmos. Artists, poets, and dreamers would create new myths, new songs, new visions. Even our sense of responsibility might change. If there is life beyond Earth, then the way we treat our own planet becomes even more urgent. We are not the sole caretakers of biology. We are one branch of a far greater tree. Life on Mars would be a mirror, showing us that Earth is not exceptional but part of a wider story. A story that is still unfolding. If life existed on Mars, even once, it would revolutionize our understanding of the cosmos. Because Mars is close. It shares our sun, our neighborhood, our history. If two worlds, side by side, both birthed life, then the universe must be teeming with it. Imagine the odds. If life were truly rare, confined to 1 in a billion planets, then Earth and Mars both hosting it would be nearly impossible. The fact that it happened here and there would mean that life is not a fluke. It is a pattern, a destiny written into the chemistry of the universe. And if Mars had life, what of Europa, with its underground oceans beneath an icy shell? What of Enceladus, spraying water vapor into space? What of Titan, with lakes of methane and complex organic molecules? Each of these worlds becomes not just interesting, but urgent. If Mars could, why not them? Even exoplanets, worlds orbiting distant stars, take on new meaning. Already, telescopes detect Earth-sized planets in habitable zones, with atmospheres rich in potential. If life can arise twice in one solar system, how many civilizations might exist across a galaxy of 400 billion stars? Mars, then, is not just about Mars. It is about everything. About whether we are alone, or whether the cosmos is filled with voices waiting to be heard. The discovery of Martian life, even a single microbe, fossilized or alive, would not just be a scientific milestone. It would be a cosmic awakening. The universe would no longer be silent. It would be alive. Our fascination with Mars did not begin with rovers or rockets. It began with telescopes, with the first astronomers who turned glass lenses toward the red point in the night sky. In the late 19th century, Italian astronomer Giovanni Schiaparelli mapped what he called canali, channels across the Martian surface. Misinterpreted as canals, these markings sparked a frenzy. The American astronomer Percival Lowell became convinced that intelligent beings had built massive waterways to survive on a dying world. His writings captivated the public, igniting stories of Martians in literature and film. As telescopes improved, the canals faded from view, revealed as optical illusions. But the idea of Mars as a living world remained. In the 20th century, science fiction writers like H.G. Wells and Ray Bradbury kept the dream alive, imagining civilizations beneath the red skies. Reality came crashing down in 1965, when NASA's Mariner 4 flew past Mars. Its images showed a barren, cratered desert, more like the moon than Earth. The vision of lush Martian landscapes collapsed overnight. And yet, hope persisted. Viking landers in the 1970s tested Martian soil for signs of life and produced ambiguous results that scientists still debate today. Then came the rovers, Pathfinder, Spirit, opportunity, curiosity. Each revealed a little more. Ancient riverbeds, salty minerals, clays formed in water. Mars was not dead, at least not always. Now, with Perseverance and its companion helicopter Ingenuity, we stand at the edge of answers once only dreamed of. Mars has shifted from myth to measurable reality. And the question that haunted Lowell and Schiaparelli remains: is Mars a world alone? Or is it, like Earth, a world of life? In the search for life on Mars, technology is our greatest ally. Every mission carries instruments more advanced than the last, designed to peel back the layers of the planet's mystery. Perseverance, for example, is equipped with Sherlock, an instrument that uses lasers and cameras to identify organic compounds at microscopic scales. It has PIXL, capable of analyzing the chemistry of rocks with pinpoint precision. It carries microphones, letting us hear the Martian wind for the first time. But machines alone cannot solve the puzzle. They must be guided by intelligence, both human and artificial. Increasingly, artificial intelligence helps rovers navigate, analyze, and prioritize. It allows them to adapt, to avoid obstacles, to seek out the most promising samples without constant instructions from Earth. This partnership between human curiosity and machine precision defines modern exploration. We cannot be everywhere, but our tools extend our senses across millions of miles. AI becomes our scout, our filter, our silent companion in the Martian dust. In the future, this alliance will deepen. Imagine fleets of autonomous drones mapping Mars from the air, or robotic drills plunging kilometers beneath the surface to sample hidden aquifers. Imagine AI-driven laboratories on Mars, analyzing data in real time, sending results back to Earth. Machines are not replacing human explorers, they are paving the way. When astronauts finally arrive, it will be because our robotic pioneers prepared the ground, found the landing sites, stored the samples. Mars is not conquered by strength, but by patience, precision, and partnership between human and machine. The idea of living on Mars is more than science fiction. It is a vision debated in laboratories, governments, and private space companies. Mars offers challenges unlike any other frontier. Its air is thin, composed mostly of carbon dioxide. Temperatures plummet at night to deadly lows. Dust storms can engulf the planet, blotting out the sun for weeks. Radiation from space rains down unshielded, slowly damaging cells and electronics alike. Yet, despite all this, Mars is the most Earth-like planet we know. It has 24-hour days. It has seasons, polar ice caps, and gravity strong enough to keep our bodies from wasting away entirely. It is difficult, but not impossible. Already, companies like SpaceX envision fleets of rockets carrying settlers. Scientists imagine domes, underground habitats, even cities built into cliffs for protection. Life support systems would recycle air and water. Greenhouses would grow food under artificial light. Eventually, industries might mine the Martian soil, producing bricks, metals, and fuel. To make Mars a second home would be to write a new chapter in human history, not as visitors, but as residents of another planet. Children could be born on Mars, their first sight not of Earth's blue skies, but of a pale pink horizon. Their games played in low gravity, their culture shaped by a dual identity, Martian and human. Yet colonizing Mars is not only about survival. It is about perspective. To live on two worlds would mean humanity had outgrown the limits of one. It would mean that even if disaster struck Earth, our story would continue. Mars would become our insurance policy against extinction, and perhaps one day the launchpad for journeys to the stars. With every great leap forward comes an ethical weight. On Mars, that weight is enormous. If life already exists there, even microbes clinging to survival in underground brines, then every human step risks contamination. Our presence could overwhelm native ecosystems, introducing Earth bacteria that outcompete fragile Martian organisms. The result might be the erasure of the very life we sought to discover. Scientists debate this fiercely. Some argue for planetary protection, strict protocols to minimize contamination, even limiting human exploration until we know more. Others counter that exploration itself requires risk, and that waiting forever could mean losing the chance to discover anything at all. The dilemma cuts deeper when we speak of colonization. Terraforming Mars, altering its air and climate, could make it habitable for us, but uninhabitable for whatever biology exists now. Would we, in our ambition, extinguish an alien species without even knowing it? The ethical challenge is not abstract. It is immediate. Every drill, every rover, every rocket launched toward Mars forces us to balance curiosity with caution. Humanity must ask itself, are we caretakers of the cosmos, or are we conquerors? The answer may define not just our relationship with Mars, but our legacy among the stars. Technology can carry us to Mars, but what about the human spirit? What happens to a person living years away from Earth, in a landscape more barren than the Moon? Psychologists already study this through analog missions on Earth, crews living in isolation in desert domes, simulating life on Mars. They measure stress, loneliness, group dynamics. Even on Earth, with rescue only hours away, the strain is real. On Mars, communication with Earth will lag by up to 22 minutes one way. No real-time conversation, no instant help. Settlers will live with the knowledge that they are utterly alone, separated not just by space but by time. The social challenges are just as immense. How do you build community when every mistake can be fatal? How do you raise children in gravity 38% of Earth's? How do you create art, culture, and joy in a world of dust and silence? Yet history gives us reason to hope. Humans adapt. From the ice of Antarctica to the deserts of Arabia, we have built lives in places that seemed unlivable. On Mars, too, people will sing, tell stories, paint on cave walls, and make meaning. The first Martian society may be fragile, but it will also be profound. It will be humanity's first step toward becoming a multiplanetary species. And with it, we will discover not just the limits of our bodies, but the resilience of our minds. Mars is not the end of the journey. It is the beginning. For centuries, humanity has gazed upward and wondered if we could ever reach the stars. The distances are daunting, trillions of miles, centuries of travel. Yet every great journey begins with a single step, and Mars is that step. By learning to live on another planet, we prepare ourselves for greater voyages. The technologies developed closed-loop life support, radiation shielding, sustainable farming in barren soils will serve not only Mars, but future missions to icy moons and beyond. Mars also offers a launching ground. With its lower gravity, rockets could depart more easily than from Earth. One day, Mars may become the shipyard of interstellar exploration, building vessels that will sail into the Black Sea of space. But beyond the practical lies the symbolic. By reaching Mars, we prove that we are not bound to Earth forever. We are not prisoners of our birthplace. We are participants in a cosmic story that stretches across time and distance. When the first Martian settlers look up at the night sky, they will see Earth as a pale blue star, fragile and beautiful. And they will know this is how it begins. Humanity's first steps away from home, on a path that may one day lead to the stars. Science is a long road of patience. For decades, we have inched forward, collecting clues on Mars. Dry riverbeds, mineral veins, organic molecules, methane plumes, leopard-spotted rocks. Each one has whispered the same possibility. But possibility is not proof. Proof in science is sacred. It must withstand doubt, replication, and relentless scrutiny. The day evidence of Martian life crosses that line will not come lightly. It will require samples drilled from untouched rock, instruments sealed against contamination, and laboratories on Earth working in unison. When the threshold is crossed, when the evidence can no longer be explained away, the world will hold its breath. We have felt this before. When Copernicus showed that Earth was not the center of the universe, humanity was shaken. When Darwin revealed our kinship with animals, worldviews cracked. When Einstein bent space and time, our reality expanded. Each time, the world resisted, debated, and then slowly changed. Martian life will be the next such revolution. Religious traditions will wrestle with the meaning. If life is everywhere, what does that say about creation, about purpose, about humanity's place? Philosophers will debate whether microbes on Mars are kin or alien. Scientists will argue about definitions. Does a cell without DNA count as life? Does it matter if it cannot evolve as we do? Governments will face choices. If Mars has life, do we dare colonize it? Can we ethically terraform a living planet? International law, vague at best, will be tested. Planetary protection, once a guideline, will become a moral imperative. For the public, the reaction will be raw and immediate. Some will celebrate, posting images of Martian microbes on every screen, turning them into memes, into symbols of wonder. Others will doubt, calling it a hoax, demanding more proof. Still others will feel fear that if life exists next door, what of the rest of the galaxy? The media storm will be unprecedented. Headlines screaming, "We are not alone." Documentaries produced within weeks. The first blurry microscope image of a Martian cell will become as famous as the Apollo 11 footprint. Children will carry it on lunchboxes and t-shirts. But amid the chaos, something deeper will stir. For the first time, every human being will know life is not Earth's monopoly. The universe is more alive than we ever dreamed. And that knowledge will not just change science. It will change us. History will remember the day, not as another scientific paper, not as a quiet announcement lost among the noise of news, but as a turning point, a before and after moment in the story of humanity. It will begin quietly, perhaps in a laboratory late at night, as a researcher leans over a microscope. A strange pattern. Cells, filaments, or a fossil appears in the sample returned from Mars. Or it may arrive as a sudden spike of data from a rover, a biosignature unmistakable and undeniable. The message will travel across cables and satellites, and within hours, it will circle the world. Screens in New York, Beijing, Nairobi, London, Sao Paulo, Sydney, all will carry the same words. Life discovered on Mars. People will stop in the streets. Cars will pull over. Offices will fall silent. For an instant, humanity will stand still, bound together by awe. And then the questions will pour forth. What does it look like? Is it alive now or fossilized? Could it be dangerous? How did it survive? News networks will scramble. Scientists who once worked in obscurity will be thrust into the spotlight, their voices broadcast to billions. Religious leaders will speak of creation in new tones. Poets will search for words that feel large enough to capture the moment. Children will ask their parents, "Does this mean aliens are real?" And the parents, for the first time, will answer, "Yes." This discovery will not be a local event. It will not belong to one nation or one agency. It will belong to everyone all at once. For in that instant, humanity will learn we are not the only life in the universe. We are part of something larger, something alive. Mars is more than a planet. It is a library written in stone, a cosmic lesson book opened for us to read. And what it teaches is not simple. It is a story of abundance and loss, of possibility and fragility. Mars shows us that habitability is fleeting. Once, rivers ran across its surface, carving valleys and deltas. Once, lakes shimmered beneath its skies. Once, a magnetic field shielded it from cosmic winds. But that protection failed. The field collapsed, the atmosphere thinned, and the waters vanished into ice and vapor. Mars became a desert. For Earth, this lesson is urgent. We too rely on fragile balances, our magnetic field, our climate, our thin blue atmosphere. Mars whispers a warning, change these and life can vanish. But Mars also teaches resilience. If life endured there, clinging beneath the surface, surviving through radiation and cold, then life is tougher than we dream. It means that biology is not a fragile miracle, but a persistent force, capable of adapting, enduring, even thriving in places that seem impossible. Mars teaches humility. If microbes once swam in Martian seas, then Earth was not first. Life has risen at least twice in our own solar system. This changes everything. It means life may be common. It means that the universe does not hesitate to produce biology when given the chance. And Mars teaches us about responsibility. For if we find living organisms there, we face a choice. Do we protect them, or do we consume their planet for ourselves? Do we treat Mars as a museum, a sanctuary, or a frontier to conquer? Every step we take on Mars will reflect who we are as a species. Colonizers, destroyers, explorers, or guardians. Mars holds up a mirror, and what we see will define us. The discovery of life on Mars will not end with science. It will reach into philosophy, politics, culture, and even personal identity. We will begin to see ourselves differently. For centuries, we have believed that Earth is exceptional, the one oasis, the singular cradle of life. But if life arose on Mars too, then it is not a miracle of Earth, it is a property of the universe itself. Life is not rare, it is the rule. This realization will ripple through every belief system. Some religions may see it as confirmation of divine abundance, that creation is vast and filled with living worlds. Others may struggle, forced to rethink humanity's role in the cosmic story. For science, the implications are staggering. If life emerged twice in one solar system, then across the galaxy, with its hundreds of billions of stars, life must be everywhere. Intelligent civilizations become not a question of if, but where. For culture, it will shift art, literature, and imagination. The Martian microbe or fossil or cell will become a new symbol of hope, a reminder that we are not isolated, but connected across planets. And for politics, the discovery will be transformative. Nations will argue over access to Mars, to its resources, to its life. New treaties will be written. Laws will be tested. Colonization will no longer be about rocks and ice, but about living ecosystems. But perhaps the greatest change will be internal. For the first time, humanity will look at the night sky and know, truly know, that we are not unique. That we are not the sole expression of biology. That we belong to a cosmos already alive. And in that knowledge, we will be called to maturity. To treat life, wherever we find it, with reverence. to see ourselves not as rulers, but as participants in a living universe. Deep beneath Martian stone, in layers untouched for billions of years, the answer waits. It may be the fossil of a bacterium etched into mineral. It may be a living microbe dormant yet enduring. Or it may be something stranger, life unlike any on Earth. Whatever it is, the moment we find it, we will change. Humanity will look back on the journey, on Viking, Pathfinder, Spirit, Opportunity, Curiosity, Perseverance, Ingenuity, and the missions yet to come. We will remember the decades of searching, the patient work of engineers and scientists, the dreams of children who looked at the red planet and asked, "Is there someone there?" And we will see Mars not just as a world of dust and rock, but as a chapter in the story of life itself. Mars is a warning, a mirror, and a promise. A warning that worlds can die, a mirror of our own fragile beginnings, and a promise that life is not alone. The discovery of Martian life will not be the end of the story. It will be the beginning of a new era of exploration, of humility, of wonder. The beginning of a search that will not stop at Mars, but will stretch outward to Europa, Enceladus, Titan, and beyond. We will no longer ask, "Are we alone?" Instead, we will ask, "Where else is life waiting?" And in that question lies humanity's destiny. For the universe is not silent. It is alive. And Mars is the first world to tell us so.